Hi there, lesson 9, and lesson 9 is about three remarkable interactions that take place in particle physics. Okay, beta decay, formation of neutrinos, pair production, and pair annihilation. Okay, so we start with beta decay, which is this we've referred to it a few times. Is this bizarre idea that electrons come out of the nucleus. So what happens in the nucleus is that a neutron changes into a proton and an electron. Okay, so that's what happens, and you've already done calculations on this, and you've written the nuclear equation. So we'll write down the nuclear equation here again. Okay, so the neutron, we know that's 0, 1, decays into, so nothing else happens, decays into proton plus electron. Okay, now what happened was, when this interaction took place, okay, they found a problem in that the energy before was not equal to the energy after, and they also found that the momentum before was not equal to momentum after. Now we don't have to go into detail, but basically it looked like the principal conservation of energy and the principal conservation of momentum were gone. Okay, and this was bad news. Okay, and we had to come up with a solution. Okay, so what happened was, this guy called Pauli decided that perhaps the issue was that there was another particle that we couldn't see at the moment that was also being produced, and that particle carried away the missing energy and momentum. Okay, and it was going to be a neutral particle with almost no mass or with no mass. Right, so there was going to be this particle. In 1931, the neutron was discovered, and a year later, Enrico Fermi, who would be Italy's greatest ever physicist, came up with the idea of beta decay. And in his idea of beta decay, he used this weird particle, okay, and he said it was a neutral particle. And people said, is that the neutron that has just been discovered by Chadwick in England? And he said, no, it's much smaller than a neutron. And as we know in Italy, if something is small, they put in ino at the end of it. So instead of calling it a neutron, he called it a neutrino. Okay, so that's where neutrino comes from, a little neutral one. Okay, so it's a little neutral one. And the symbol for it is nu. Okay, which is that, a bit like a V. Okay, Greek letter. Okay, and as it turns out, and we'll come back to this later, it wasn't just a neutrino, it was an antineutrino. And anti, you put a line on top of it or a bar. Okay, it's called the antineutrino. If you don't put in the bar, it doesn't matter. Okay, neutrino, antineutrino, no big deal. Okay, so this is what's happened. Okay, now, so basically we want to look at what's actually happening then in the nucleus when this happens. So if we just draw a kind of a random nucleus, and we call them the protons. Oh, that's not good news. A red one. Okay, and these are the neutrons. Okay, so let's think about it. Okay, if a neutron, which is the red one, decays into a proton. So watch what happens, it's important. The neutron changes into a proton. Okay. Now, think about it. The mass number hasn't changed. A neutron has changed into a proton. There is no change in the mass number. Okay. The mass number hasn't changed, but the charge of this has gone up by 1. Okay, because the neutron has changed to a proton. So the atomic number has gone up by 1. The mass number hasn't changed for the daughter nucleus. And also there's an electron, and the electron is emitted. Okay, and as it turns out, there's this neutrino, which is also emitted, okay, which we'll see happening later, okay. But let's look at it. Okay, the mass number stays the same. Okay, the daughter nucleus, the atomic number goes up by 1, not down by 1. So let's take an example. We've seen a few examples, but one of them was carbon 14. Right, and carbon 14 becomes nitrogen 14. Think about it. One of the neutrons has become a proton, so we have one extra proton. We've lost a neutron, gained a proton, so no change in the mass. Also an electron emitted, and also, to be very posh about it, we put in the neutrino at this stage, okay? And the important thing is, why was the neutron proposed? Because there was a missing momentum and charge, and that provided the missing charge momentum. The principal conservation of energy, the principal conservation of momentum were saved, okay, and we were all happy again. That's step 1. That's beta decay. We need to be clear on that, okay? Now step 2 is pair production and step 3 is pair annihilation. They're both very similar, as we'll see. Now, so it becomes very interesting, okay, in that we have particles, and we'll talk about them in more detail next week, called antiparticles, okay, and we just mentioned one there, the antineutrino. And effectively, a particle's antiparticle, they have different properties, but the one that we're most interested in is charge. So we have an electron, and it has an antiparticle called an anti-electron, okay, electron, anti-electron. The electron is a negative charge, the anti-electron is the same in every way, except it has a positive charge, okay, that's it, okay. So let's think about it. That's the symbol for an electron. Well, what's the symbol for an anti-electron? Symbol for an anti-electron, mass 0, 1, plus 1. That's an anti-electron. And because anti-electrons are very important, they have their special name. They're positive electrons, so they're called positrons. Okay, and as we'll see later, in hospitals, there are things called positron emission tomography machines that are used for scanning, okay, for scanning inside body and so on. So this sounds weird, but it has real life applications all the way. Okay, so so antiparticles, everything is the same for our purposes except opposite charge, right? Okay. Now, here comes the interesting part. If you have a particle and its antiparticle meet, they annihilate. Gone. Okay, they annihilate. What does annihilate mean in physics? It means they turn entirely into energy. They turn entirely into energy. Okay, so basically, if you get an electron, okay, there's your electron, there's your positron. When they meet, they disappear. The masses are gone, and their mass changes entirely into energy. Okay, now this actually happens at very low velocities, okay, and basically zero momentum, okay. So basically afterwards it has to have zero momentum again, principal conservation momentum. So instead of having one photon of energy release, because the energy will be now in the form of a photon, okay, like an X-ray or a gamma ray, okay, instead of one photon being released, because one photon would have momentum, okay, they have two photons released in the opposite directions. Okay, same idea as we had for the alpha particles yesterday. Now, someone will be saying, hold on a sec, how can I have a photon have momentum that has no mass? Photons have momentum. That's for another day. Okay, so let's look at pair annihilation for an electron, and let's go down through the nuclear equation that we have for it. Okay, so we will have an electron and a positron. They come together. We'll come into the detail of them coming together again another day. We don't have time today because we're running late. Okay, and it decays into two photons. Now, we've two ways of writing photons. Okay, we can write it like this because they're generally gamma ray photons, or we usually instead write it like this, and we actually use, because we know the energy of a photon is HF, we use HF effectively as a symbol, just as a symbol like that. This is not the maths equation. We'll have the maths equation later on paper. Okay, we just use it like that. So that's it. Pair annihilation. All of the mass is now energy. Okay, all the mass is now energy. It sounds science fiction. It's not. This happens in PET scanners every day of the week in hospitals to detect illnesses inside people's bodies and so on. That's pair annihilation. Okay, calculations to follow on paper. Third and final we want to look at is pair production. Okay, which is the opposite. Okay, now before we get on to pair production, remember we needed two photons here to conserve momentum. Two photons, why? Two photons of pair annihilation to conserve momentum. Right? Now pair production is, as you can imagine, the opposite. Now this is even more bizarre, okay, because you get a photon and the photon turns into two particles. So you have energy, packet of energy, two particles, okay, right? Again, let's have a look at it. Now what happens here is, just kind of in general terms, you get a photon, the photon hits a nucleus. The nucleus is almost like a catalyst, okay, in that the nucleus isn't involved, okay. What happens is the photon is absorbed by the nucleus and a particle and antiparticle are emitted. The nucleus stays there, so we can ignore the nucleus. So effectively what happens is a photon comes in, particle and antiparticle goes out, okay. So basically the energy of the photon is converted into mass. All of the energy of the photon converted into mass, okay. Now let's go through there is an issue here regarding principal conservation of charge, which is relevant to this one. Okay, so we have this time the photon comes in and it turns into, now if it just turned into an electron, there's a problem, because look at it. Beforehand the charge is 0, because photons have no charge. Afterwards the charge is -1. That can't be. We have a principle of conservation of charge which we've been dealing with all along with nuclear equations, because the atomic number, which is the charge, is always the same on the left as on the right. Still has to be the case here. So you can't make an electron by pair production. No, there's a reason it's called pair, as you could guess. Pair production, you can't make an electron, you have to make a particle-antiparticle pair. So in other words, if you're making an electron, you make a positron as well. So we have this plus the positron, which is the same but charge +1. Now we're in business. It's the reverse, basically, of the pair annihilation, but there is a difference. 1 photon. Okay, and look what happens. A photon is absorbed by a nucleus, and then the electron and the photon are emitted. Now they're actually kind of emitted in opposite directions. That's not a good diagram. They're emitted, okay, and that's basically, that's it. So they're the three: beta decay, pair annihilation, pair production. Step 2, we're going to look at it on paper with some calculations for annihilation and production, and in step 3 we'll go through it in the notes, and the notes kind of gives us a flavour for it. And in step 4 they're going to give you little video clips to have a look at what's going on as well, and that'll be the job for the weekend. Okay, see you in a minute.